What if everything you thought you knew about reality was just the surface of something far stranger, far more mysterious? Imagine a world where particles can exist in multiple places at once, where objects can be connected across vast distances instantaneously, and where the very act of observing something can change its behavior. This isn't science fiction, it's the bizarre and mind-bending world of quantum mechanics. For decades, scientists have been uncovering anomalies that defy our everyday understanding of how the universe works. These aren't just quirks of physics, they're clues that suggest a reality far beyond what we can perceive. In this video, we're diving into 32 of the most astonishing quantum anomalies phenomena that challenge everything we think we know about space, time, and existence itself. From particles that seem to communicate faster than the speed of light to experiments that reveal the universe might be more like a cosmic simulation than a fixed reality, each of these anomalies points to a deeper, more mysterious truth. What if the universe isn't as solid and predictable as it seems? What if the rules we live by are just the tip of the iceberg? Over the next few minutes, we'll explore these strange and fascinating discoveries, uncovering how they might reshape our understanding of reality. Get ready to question everything you thought you knew, because the quantum world is about to take you on a journey into the unknown. Let's begin. One of the most famous and puzzling experiments in quantum mechanics is the double-slit experiment. Picture this: you have a barrier with two narrow slits and you shoot tiny particles like electrons toward it. If you don't observe the particles as they pass through the slits, they behave like waves, creating an interference pattern on the other side. But here's where it gets weird. If you set up a detector to observe which slit each particle goes through, the particles suddenly start acting like single, discrete points, and the interference pattern disappears. It's as if the particles know they're being watched and change their behavior accordingly. This experiment reveals something extraordinary. The act of observation itself seems to influence reality. Think of it like a camera in a dark room. Without the camera, the room exists in a kind of fuzzy, undefined state. But the moment you turn on the camera, the scene snaps into focus. The double-slit experiment suggests that, on a quantum level, reality isn't fixed until someone or something observes it. This raises profound questions about the role of consciousness in shaping the universe. Are we merely passive observers, or do we somehow play a part in creating the reality we experience? The implications of this anomaly are staggering. If particles can exist in multiple states at once until observed, what does that say about the nature of reality itself? It's as if the universe is waiting for us to look before deciding how things should be. This experiment doesn't just challenge our understanding of physics, it blurs the line between the observer and the observed, hinting at a deeper connection between mind and matter. And if this seems strange, just wait. It's only the beginning of the quantum rabbit hole. What comes next is even more mind-bending. Now, let's take a step deeper into the quantum rabbit hole with one of the most perplexing phenomena in all of physics: quantum entanglement. Imagine you have two coins. You flip them at the same time, and no matter how far apart they are, whether they're in the same room or on opposite sides of the galaxy, they always land on the same side. Heads or tails, they're perfectly in sync. This is the essence of quantum entanglement, where two particles become inexplicably linked, sharing a connection that defies space and time. In the quantum world, when particles become entangled, their properties like spin or polarization become intertwined. Measure one, and you instantly know the state of the other, no matter the distance between them. This connection happens faster than the speed of light, which, according to Einstein's theory of relativity, should be impossible. Einstein himself famously called this spooky action at a distance, as it seemed to break the rules of classical physics. But here's the kicker. Experiments have repeatedly confirmed that entanglement is real, and it's every bit as strange as it sounds. What makes this phenomenon so baffling is that it suggests a hidden layer of interconnectedness in the universe, a kind of cosmic web that binds particles together in ways we can't fully comprehend. It's as if the universe is playing a game where the rules aren't just hidden, they're entirely different from what we're used to. This isn't just about particles communicating instantaneously. It's about the very fabric of reality being far more intertwined than we ever imagined. And if entanglement leaves you scratching your head, consider this. It might only be the tip of the iceberg. The quantum world is full of surprises, and entanglement is just one piece of a much larger puzzle. What other secrets might be waiting to be uncovered? As we delve further into these anomalies, the mysteries only grow deeper. Next, we'll explore how these entangled particles might be hinting at something even more extraordinary, a reality where the universe itself could be a vast, interconnected network. Stay tuned, because the quantum journey is about to get even stranger. Now, let's turn our attention to one of the most iconic and perplexing thought experiments in quantum physics, Schrödinger's cat. Imagine this. You place a cat inside a sealed box along with a tiny bit of radioactive material, a Geiger counter, and a vial of poison. If the Geiger counter detects radioactive decay, the vial breaks and the cat dies. But here's the twist. Until you open the box and observe the cat, it exists in a bizarre state of being both alive and dead at the same time. This is the essence of quantum superposition, where a system can exist in multiple states simultaneously until it's measured or observed. To make this more relatable, think of it like ordering a package online. Until you check your doorstep, the package exists in a kind of quantum limbo. It's both delivered and undelivered. The moment you open your door and look, the package status collapses into one definite reality. Either it's there or it isn't. Schrödinger's cat is the quantum version of this scenario, but instead of a package, it's a living creature, and instead of a doorstep, it's a sealed box governed by the strange rules of quantum mechanics. At first glance, this might seem like a purely theoretical exercise, but it reveals something profound about the nature of reality. Superposition suggests that particles, and by extension, entire systems, don't have definite properties until they're observed. This challenges our everyday intuition, where objects exist in clear, defined states. In the quantum world, reality is fluid, and the act of observation is what solidifies it. It's as if the universe is holding its breath, waiting for someone to look before deciding how things should be. But what does this mean for us? If superposition applies to particles, could it also apply to larger objects, or even us? While the thought of a cat being both alive and dead is unsettling, it's a vivid illustration of how the quantum world operates on principles that seem almost alien compared to our macroscopic experiences. And yet, these principles aren't just abstract ideas, they're the foundation of technologies like quantum computing, which rely on superposition to perform calculations at unimaginable speeds. Schrödinger's cat isn't just a quirky thought experiment, it's a window into the strange and counterintuitive nature of quantum mechanics. It forces us to confront the idea that reality might not be as solid or predictable as we think. And while superposition is mind-bending on its own, it's just one piece of a much larger puzzle. As we continue to explore these quantum anomalies, we'll uncover even more ways in which the universe defies our expectations, reshaping our understanding of what's possible. The next anomaly we'll examine takes this strangeness even further, so hold on tight, because the quantum journey is far from over. Now, let's explore a phenomenon that sounds like it's straight out of a science fiction novel: quantum tunneling. Imagine throwing a ball at a solid wall. In the everyday world, the ball would bounce back, no question about it. But in the quantum realm, particles can do something that seems utterly impossible. they can pass through barriers as if they weren't even there. It's like watching a ghost glide through a wall, defying everything we think we know about physical boundaries. To make this clearer, picture a ball rolling up a hill. If the ball doesn't have enough energy to reach the top, it would normally roll back down. But in the quantum world, there's a chance, albeit a small one, that the ball could suddenly appear on the other side of the hill, as if it had magically tunneled through it. This is quantum tunneling, and it's not just a theoretical curiosity. It's a fundamental aspect of how particles behave at the smallest scales. So, how does this work? In quantum mechanics, particles don't have definite positions until they're observed. Instead, they exist as waves of probability spreading out in space. Sometimes these probability waves extend beyond barriers, creating a small but real chance that the particle can tunnel through to the other side. It's not that the particle is breaking the laws of physics, it's that the rules of the quantum world are just different from what we're used to. This bizarre behavior has profound implications, especially for technology. Quantum tunneling is at the heart of devices like flash memory and modern electronics, where it allows electrons to pass through barriers that would otherwise block them. It's also a key principle in quantum computing, where tunneling enables qubits to exist in multiple states simultaneously, unlocking unprecedented computational power. Without tunneling, many of the technological advancements we rely on today simply wouldn't exist. But the implications go even deeper. Quantum tunneling suggests that the universe operates on a set of rules that are far more flexible and far stranger than our classical intuition would allow. It hints at a reality where barriers aren't as solid as they seem, where particles can slip through the cracks of space and time, and where the boundaries we take for granted might not be so absolute after all. What if these quantum anomalies, tunneling, superposition, entanglement, are all pointing to a deeper truth about the fabric of reality? Could they be glimpses of a universe that's far more interconnected, far more fluid than we've ever imagined? As we delve further into these mysteries, the answers only seem to raise more questions, and the next anomaly we'll explore takes us even closer to the edge of understanding, where the very nature of time and space begins to unravel. Stay tuned, because the quantum journey is about to get even more fascinating. Let's shift our focus to one of the most intriguing concepts in quantum mechanics, the observer effect. Imagine a shy performer who only steps onto the stage when the lights are on and the audience is watching. Without an audience, the performer remains hidden, as if the show doesn't exist. This is eerily similar to how particles behave in the quantum world. Until they're observed, particles seem to exist in a nebulous state of possibilities, almost as if they're waiting for someone to look before deciding what to do. This phenomenon isn't just a quirky detail, it's a cornerstone of quantum mechanics. The observer effect reveals that the very act of measuring or observing a particle can fundamentally alter its behavior. Take the double-slit experiment we discussed earlier. When particles aren't being watched, they act like waves, spreading out and creating an interference pattern. But the moment you observe them, they snap into definite positions, behaving like discrete particles instead. It's as if the particles are aware of being watched and adjust their behavior accordingly. This raises a profound question. Does reality exist independently of observers? In the macroscopic world, we assume that objects have definite properties whether we're looking at them or not. A tree in a forest, for example, doesn't need someone to observe it to exist. But in the quantum realm, the rules seem to flip. Particles don't have fixed properties until they're measured, suggesting that observation might play a crucial role in shaping reality itself. This idea blurs the line between the observer and the observed, hinting at a universe where consciousness and matter are deeply intertwined. The philosophical implications of this are staggering. If observation is necessary to collapse a particle's wave function into a definite state, does that mean reality is subjective? Could it be that the universe is a kind of participatory phenomenon, where observers are not just passive witnesses but active participants in creating the world around us? These questions challenge our very understanding of existence, pushing us to reconsider the nature of reality and our place within it. But the observer effect isn't just a philosophical puzzle, it has practical implications too. Technologies like quantum computing rely on our ability to manipulate and measure particles in specific ways, leveraging their strange behavior to perform calculations that would be impossible with classical computers. Understanding how observation affects particles is key to unlocking the potential of these groundbreaking technologies. As we ponder the observer effect, it's hard not to wonder, could observation itself be a fundamental force in the universe? Just as gravity shapes the motion of planets and electromagnetism governs the behavior of charged particles, might the act of observing be a force that shapes the fabric of reality? This idea takes us to the edge of what we know, hinting at a universe that's far more interconnected and far stranger than we've ever imagined. And as we continue our journey through these quantum anomalies, the mysteries only grow deeper, inviting us to explore the very boundaries of reality itself. Let's dive into one of the most mind-bending concepts in quantum mechanics, wave-particle duality. Picture a chameleon blending perfectly into its surroundings. In one environment, it might appear green, while in another, it could shift to brown or even blue. Its appearance changes depending on the context, yet it's still the same creature. Now, imagine particles like electrons or photons behaving in a similar way. Depending on how you observe them, they can act like waves or particles, two seemingly contradictory behaviors that defy our classical understanding of matter. In the classical world, we're used to objects having clear, distinct properties. A ball is a ball and a wave is a wave, but in the quantum realm, particles don't play by these rules. When you set up an experiment to measure a particle's position, say, by firing it through a slit, it behaves like a tiny, discrete point hitting a specific spot on a detector. But if you set up an experiment to measure its wave-like properties, like in the double-slit experiment, it spreads out and creates an interference pattern, as if it's a wave passing through both slits at once. It's as if the particle is constantly shifting its identity based on how you're looking at it. This duality isn't just a quirk of quantum mechanics, it's a fundamental aspect of how particles behave. Think of it like this: a particle is neither purely a wave nor purely a particle. Instead, it exists in a kind of quantum limbo, capable of exhibiting either behavior depending on the circumstances. It's almost as if the universe is saying, you want to see a particle, here's a particle. You want to see a wave, here's a wave. But what you're really seeing is just one side of a much more complex, multifaceted reality. This idea challenges everything we thought we knew about the nature of matter. In the classical world, objects have fixed properties. A table is solid, a beam of light is a wave. But in the quantum world, the rules are fluid, and the very act of measurement can change what you're measuring. It's a bit like trying to describe a chameleon by only looking at it in one setting. You might think it's green, but step into a different environment and suddenly it's brown. The chameleon hasn't changed, it's still the same animal, but your perception of it has. So, what does this mean for our understanding of reality? Wave-particle duality suggests that the universe operates on a level far more nuanced than our everyday experiences can capture. It forces us to rethink how we define matter, energy, and even existence itself. Could it be that particles are neither waves nor particles, but something else entirely, something our current language and theories can't fully describe? This duality is a reminder that the quantum world is full of surprises. and that our classical intuitions might only scratch the surface of what's really going on. But here's the thing, wave-particle duality is just one piece of a much larger puzzle. It's a clue that points to a deeper, more interconnected reality, one where the boundaries between waves and particles, between matter and energy, are far blurrier than we ever imagined. As we continue to explore these quantum anomalies, we'll uncover even more ways in which the universe defies our expectations, pushing us to rethink not just physics, but the very nature of reality itself. And the next anomaly we'll explore takes this strangeness even further, revealing a universe that's even more interconnected and mysterious than we thought possible. Let's step into the strange and fascinating world of quantum superposition, where particles defy the rules of the everyday world. Picture a spinning coin. While it's in the air, it's neither heads nor tails, it's both at the same time. It's only when the coin lands that it chooses a definite state. Now, imagine that same principle applying to particles in the quantum realm. Instead of coins, we're talking about electrons, photons, or even atoms that can exist in multiple states simultaneously until they're measured or observed. This isn't just a theoretical idea, it's a fundamental feature of quantum mechanics. In the quantum world, particles don't have to pick a single state. An electron, for example, can spin in multiple directions at once, or a photon can exist in multiple positions simultaneously. It's as if the universe is holding its breath, keeping all possibilities open until the moment of observation forces a decision. This concept might sound like science fiction, but it's a well-documented phenomenon that has been confirmed through countless experiments. The implications of superposition are profound, especially when it comes to technology. Take quantum computing, for example. Classical computers rely on bits, which can be either a 0 or a 1. But quantum computers use qubits, which can be 0, 1, or both at the same time, thanks to superposition. This allows quantum computers to perform complex calculations at speeds that would be impossible for traditional machines. It's like solving a maze by exploring every possible path simultaneously, rather than taking one path at a time. This capability could revolutionize fields like cryptography, medicine, and artificial intelligence, opening doors to discoveries we can't yet imagine. But superposition isn't just about computing power, it's also reshaping how we think about reality itself. If particles can exist in multiple states until observed, what does that say about the nature of existence? Could it be that reality itself is a kind of quantum soup, with all possibilities existing simultaneously until someone or something takes a look? This idea challenges our classical view of a fixed, objective universe, suggesting instead that reality might be far more fluid and dynamic than we've ever realized. And here's where things get even more intriguing. If superposition applies to particles, could it also apply to larger objects or even us? While we don't experience superposition in our everyday lives, the fact that it exists at the quantum level raises tantalizing questions about the nature of consciousness, perception, and the fabric of reality itself. Are we, too, part of this quantum dance, with our observations playing a role in shaping the world around us? As we grapple with these questions, one thing becomes clear: superposition isn't just a quirk of quantum mechanics. It's a window into a deeper, more interconnected reality, one where the boundaries between possibilities are far blurrier than we ever imagined. And as we continue to explore these quantum anomalies, we'll uncover even more ways in which the universe defies our expectations, challenging us to rethink not just physics, but the very nature of existence. Now, let's venture into a principle that lies at the heart of quantum mechanics, a concept so profound that it reshapes how we think about measurement, knowledge, and the very nature of reality itself. This is Heisenberg's uncertainty principle, and it tells us something startling. there's a fundamental limit to what we can know about the universe. Specifically, the principle states that we cannot simultaneously know both the position and momentum of a particle with absolute precision. The more precisely you measure one, the less precisely you can measure the other. It's as if the universe has built-in limits to our ability to observe it, like an unbreakable cosmic rulebook. To grasp this, imagine trying to catch a firefly on a dark summer night. The moment you focus on its exact location, where it's hovering, you lose track of how fast it's moving. Conversely, if you try to measure its speed, you can't pinpoint its exact position. The firefly flickers in and out of certainty, always staying just beyond your full understanding. This is essentially what happens at the quantum level. Particles, like that elusive firefly, exist in a state of inherent uncertainty, where the very act of measuring one aspect obscures another. But why does this happen? At its core, the uncertainty principle arises from the wave-like nature of particles. In the quantum world, particles don't behave like tiny billiard balls with fixed trajectories. Instead, they exist as probability waves spreading out in space and time. When you measure a particle's position, you're essentially collapsing its wave function to a specific point, but in doing so, you lose information about its momentum. It's not a limitation of our tools or technology, it's a fundamental feature of how the universe operates. This principle has profound implications, not just for physics, but for our understanding of reality itself. It suggests that uncertainty isn't just a quirk of quantum mechanics, it might be woven into the very fabric of existence. In the classical world, we're used to thinking of the universe as a clockwork machine where everything can, in theory, be predicted with perfect accuracy if we have enough information. But the uncertainty principle shatters that illusion, revealing a universe where unpredictability is built into the rules. What's even more fascinating is how this principle challenges the limits of human knowledge. If we can't measure both position and momentum simultaneously, does that mean there are aspects of reality that are forever beyond our reach? Could uncertainty be a fundamental feature of the universe rather than just a limitation of our current understanding? These questions push us to rethink not just physics, but the nature of knowledge itself. Are we destined to live in a world where some truths remain forever hidden? Or is there a deeper layer of reality waiting to be uncovered? The uncertainty principle also has practical implications, particularly in the field of quantum computing. By embracing this inherent fuzziness, quantum computers can perform calculations that would be impossible for classical machines, opening up new frontiers in science and technology. It's a reminder that sometimes limitations can be gateways to innovation, pushing us to think outside the box and explore uncharted territory. As we ponder the implications of Heisenberg's uncertainty principle, one thing becomes clear: the quantum world is not just strange, it's a place where the rules we take for granted no longer apply. It challenges us to embrace uncertainty, to question our assumptions, and to recognize that the universe might be far more mysterious than we ever imagined. And as we continue to explore these anomalies, we'll uncover even more ways in which the quantum realm defies our expectations, inviting us to rethink not just physics, but the very nature of reality itself. Now, let's explore a phenomenon that bridges the gap between the bizarre quantum world and the familiar classical one: quantum decoherence. Imagine a perfectly still pond, its surface so clear you can see every pebble at the bottom. This pristine state is like a quantum system in superposition, where particles exist in multiple states at once, undisturbed and full of possibilities. But what happens if you toss a stone into the pond? Ripples spread across the surface, mud rises from the bottom, and the water becomes murky. In the same way, when a quantum system interacts with its environment, whether it's air molecules, light, or even other particles, its delicate superposition collapses, and the system loses its quantum purity. This process is called decoherence, At its core, decoherence explains why we don't experience quantum weirdness in our everyday lives. In the microscopic world, particles can exist in multiple states simultaneously, but as they interact with their surroundings, those states become entangled with the environment. This entanglement effectively leaks quantum information into the world around it, causing the system to behave more like a classical object. It's as if the universe has a built-in mechanism that keeps the quantum and classical worlds separate, ensuring that the strange rules of quantum mechanics don't spill over into our macroscopic reality. But decoherence isn't just about explaining why we don't see cats both alive and dead or tables in two places at once. It also plays a crucial role in the transition from quantum to classical behavior. Think of it as a filter. As quantum systems interact with their environment, their superposition fades out, and they settle into a single, definite state. This process is what allows quantum computers to perform calculations while still being able to give us concrete results. Without decoherence, the quantum world would remain a blur of probabilities, and we'd have no way to extract meaningful information from it. What makes decoherence so fascinating is that it doesn't just explain how quantum systems become classical. It also hints at something deeper about the nature of reality. Could decoherence be the key to understanding why the quantum world behaves so differently from our own? Some scientists speculate that it might hold clues to the fundamental structure of the universe, suggesting that reality itself is shaped by the interactions between quantum systems and their environment. In this view, the classical world we experience isn't separate from the quantum one. It's an emergent property, a kind of average of countless quantum interactions. This idea takes us to the edge of what we know, inviting us to rethink not just physics but the very fabric of existence. If decoherence is the mechanism that transforms quantum possibilities into classical realities, could it also be the key to unlocking the mysteries of consciousness, perception, and the nature of observation itself? These questions push us to consider whether the universe is fundamentally quantum at its core, with the classical world emerging as a kind of illusion created by decoherence. As we reflect on this phenomenon, one thing becomes clear. Quantum decoherence isn't just a technical detail, it's a gateway to understanding the profound interplay between the quantum and classical worlds. It challenges us to see reality not as a fixed, static thing, but as a dynamic process shaped by the constant interactions between systems and their environment. And as we continue to explore these quantum anomalies, the mysteries only grow deeper, inviting us to peer even further into the strange and beautiful world of quantum mechanics. Now, let's venture into one of the most audacious and mind-expanding ideas in quantum mechanics, the many-worlds interpretation. Imagine standing at the base of an enormous tree, its branches stretching endlessly in every direction. Each branch represents a different path, a different outcome of every decision or event. In the quantum world, this isn't just a metaphor, it's a literal description of reality. According to the many worlds interpretation, every quantum event doesn't just have one outcome. It spawns an entire new universe, branching off like a new limb on that cosmic tree. To put it simply, let's say you're flipping a coin. In our everyday experience, it lands on either heads or tails, but in the many worlds view, both outcomes happen just in different universes. In one universe, the coin lands on heads, and in another, it lands on tails. And this branching doesn't stop at coin flips. Every quantum event, every choice, every interaction, every measurement creates an infinite web of parallel realities, each one slightly different from the last. It's as if the universe is constantly splitting into countless versions of itself, each one a new thread in the tapestry of existence. This idea might sound like science fiction, but it's a serious proposal that attempts to explain some of the strangest aspects of quantum mechanics, like superposition and wave function collapse. Instead of particles existing in multiple states until observed, the many worlds interpretation suggests that all possible states actually occur, they just happen in different universes. In one universe, Schrödinger's cat is alive, in another, it's dead. There's no need for a mysterious collapse of the wave function because every possibility plays out somewhere in the multiverse. But what does this mean for us? If every decision we make spawns a new universe, what happens to free will? Are we just passive observers watching as the universe splits into countless versions of itself with every choice? Or do we, in some way, shape which branch we follow? These questions blur the line between science and philosophy, challenging us to rethink not just the nature of reality, but our role within it. Could it be that every version of you, every possible outcome of your life exists somewhere in the multiverse? And if so, what does that say about the choices we make in this one? The implications of the many worlds interpretation are staggering. It suggests a universe that's not just vast but infinitely diverse, filled with endless possibilities. It also raises profound questions about the nature of existence itself. If every quantum event creates a new universe, does that mean the multiverse is constantly expanding, branching into an ever-growing web of realities? And if so, where does it all end, or does it end at all? This interpretation doesn't just challenge our understanding of physics, it reshapes how we see ourselves in the cosmos. Instead of living in a single, fixed reality, we might be part of an infinite multiverse, where every decision, every event ripples out into countless parallel worlds. It's a humbling and awe-inspiring idea, one that invites us to consider the vastness of existence and the endless possibilities that lie beyond our perception. As we grapple with these ideas, one thing becomes clear: the many worlds interpretation isn't just a theory about quantum mechanics. It's a vision of a universe that's far grander, far more interconnected, and far stranger than we've ever imagined. And as we continue to explore these quantum anomalies, we'll uncover even more ways in which the universe defies our expectations, pushing us to rethink not just physics, but the very nature of reality itself. The next anomaly we'll examine takes this interconnectedness even further, revealing a universe that's even more intertwined and mysterious than we thought possible. Now, let's explore a quantum phenomenon that feels almost like a cosmic game of freeze tag: the quantum Zeno effect. Imagine a child spinning a top on a table. As long as no one touches it, the top whirls freely, its motion smooth and uninterrupted. But what happens if you keep interrupting it, constantly checking on it or tapping it lightly? The top slows down, its energy dissipates, and eventually it stops spinning altogether. In the quantum world, something eerily similar happens when you observe a system too frequently. The act of repeated observation can effectively freeze a quantum system in a particular state, as if the universe is pausing its motion every time you take a peek. This effect gets its name from the ancient Greek philosopher Zeno, who proposed a paradox suggesting that motion is an illusion because at any given instant, an object appears frozen in place. In quantum mechanics, the Zeno effect takes this idea to a whole new level. When you measure a quantum system, say, an atom in an excited state, you collapse its wave function, forcing it into a definite state. If you measure it again and again in rapid succession, the system doesn't have time to evolve or change. It's like hitting pause on a movie every millisecond. The film can't progress because you're constantly interrupting its flow. But why does this happen? At its core, the quantum Zeno effect is a consequence of how quantum systems evolve over time. In the absence of observation, particles exist in a superposition of states, evolving according to the laws of quantum mechanics. But each measurement resets the system's evolution, effectively resetting the clock and keeping it locked in its current state. It's as if the universe is saying, if you keep looking, I'll just stay put. This effect isn't just a curious quirk of quantum mechanics. It has practical implications, especially in the field of quantum computing. By repeatedly measuring a quantum system, scientists can stabilize it, preventing it from decohering or losing its quantum properties. This stabilization is crucial for building reliable quantum computers, which rely on maintaining delicate quantum states for long periods of time. The quantum Zeno effect offers a way to freeze these states, buying scientists precious time to perform calculations without losing coherence. But here's where things get even more fascinating. If repeated observation can freeze a quantum system, what does that say about the role of observation in shaping reality? Could it be that the act of watching something, whether it's a particle or a spinning top, has a profound influence on how the universe behaves? This idea takes us back to the heart of quantum mechanics, where the line between observer and observed becomes increasingly blurred. The quantum Zeno effect is a reminder that the quantum world operates on principles that are both strange and deeply interconnected. It challenges us to rethink not just how we observe the universe, but how our observations might actively shape it. And as we continue to explore these quantum anomalies, we'll uncover even more ways in which the universe defies our expectations, revealing a reality that's far more dynamic and mysterious than we ever imagined. Now let's dive into one of the most futuristic-sounding concepts in quantum mechanics, quantum teleportation. Picture this: you're sitting in your living room and you want to send a handwritten letter to a friend on the other side of the planet. But instead of putting it in an envelope, dropping it in the mail, and waiting for it to travel thousands of miles, you simply press a button and poof. The letter instantly appears in your friend's hands. No planes, no trucks, no waiting. This is the essence of quantum teleportation, not moving an object through space, but transferring its information instantly across vast distances. At its core, quantum teleportation relies on one of the strangest phenomena we've already explored: quantum entanglement. Remember those two particles that are mysteriously linked, no matter how far apart they are? Quantum teleportation uses this connection to send information from one particle to another without physically moving anything between them. Here's how it works. Imagine you have two entangled particles. Let's call them particle A and particle B. Particle A stays with you while particle B is sent to your friend. Now, if you want to teleport information, say, the spin state of a third particle, you perform a specific set of measurements on particle A and the third particle. These measurements encode the information, which is then instantly transferred to particle B, thanks to their entangled connection. It's like sending a secret message through an invisible quantum tunnel. But here's the catch: while the information is transferred instantly, the process isn't exactly like the teleportation you see in science fiction. You can't use it to teleport physical objects or people across the galaxy. Instead, quantum teleportation is about moving quantum states, the unique properties of particles like spin or polarization. This might sound abstract, but it has enormous implications for the future of technology, particularly in fields like communication and computing. Imagine a world where sensitive information like encryption keys or medical data could be sent instantly and securely without the risk of interception. Quantum teleportation could make that possible, revolutionizing how we share and protect information. What makes this even more exciting is its potential role in quantum computing. In a quantum computer, bits of information called qubits can exist in multiple states at once thanks to superposition. But these qubits are incredibly fragile, and even the smallest interference can disrupt their delicate states. Quantum teleportation offers a way to move these qubits from one part of a quantum computer to another without losing their integrity, paving the way for faster, more powerful machines. It's like having a superhighway for quantum information, allowing data to flow seamlessly across vast networks. But quantum teleportation isn't just a technological marvel, it's also a window into the deeper mysteries of the universe. It challenges our understanding of space and time, showing that information can be transferred in ways that defy classical physics. Could this be a clue that the universe is far more interconnected than we ever imagined? Might teleportation hint at a reality where distance and separation are illusions and everything is fundamentally linked? As we marvel at the possibilities of quantum teleportation, it's hard not to wonder what other breakthroughs lie ahead. Could this be just the beginning of a new era in quantum technology, where the boundaries of space and time are no longer limits but opportunities? The journey into the quantum world is far from over, and each discovery brings us closer to unlocking the full potential of this strange and fascinating realm. Now let's turn our attention to one of the most mind-boggling concepts in quantum mechanics, the quantum vacuum. At first glance, the vacuum of space might seem like the ultimate emptiness, a vast, dark void where nothing exists. But in the quantum world, nothing is far from nothing. In fact, empty space is a seething, bubbling cauldron of activity, teeming with particles that flicker in and out of existence faster than we can blink. It's as if the universe is a calm ocean, its surface smooth and serene, while beneath the waves, a storm of energy churns endlessly. This phenomenon is known as quantum fluctuations, and it's one of the strangest predictions of quantum field theory. According to this theory, the vacuum of space isn't truly empty. It's filled with a kind of background energy, often called the zero-point energy. Out of this energy, pairs of particles and antiparticles spontaneously appear, only to annihilate each other moments later. These are called virtual particles, and they exist for such a short time that they're almost impossible to detect directly. But their effects are very real, and they play a crucial role in shaping the behavior of the universe at the smallest scales. To visualize this, think of the quantum vacuum as a pot of boiling water. On the surface, everything looks calm, but beneath the surface, bubbles are constantly forming and popping, creating a chaotic dance of energy. In the same way, the quantum vacuum is a dynamic, ever-changing field where particles are constantly being born and destroyed. This isn't just a theoretical idea, it's been confirmed through experiments like the Casimir effect, where two metal plates placed extremely close together experience a tiny but measurable force caused by the fluctuations in the vacuum between them. But what does this mean for our understanding of the universe? For one, it challenges the very idea of a true vacuum. If empty space is teeming with energy and particles, then true emptiness might be impossible. This has profound implications for everything from the structure of the cosmos to the nature of energy itself. Some scientists even speculate that the quantum vacuum could be the source of dark energy, the mysterious force driving the accelerated expansion of the universe. Could it be that the energy of the vacuum is literally pushing the cosmos apart? The quantum vacuum also raises fascinating questions about the nature of reality. If particles can pop into existence out of nothing, does that mean the universe itself could have emerged from a similar process? Could the Big Bang have been a kind of quantum fluctuation on a cosmic scale? These ideas blur the line between physics and philosophy, inviting us to rethink not just the nature of space and time, but the very origins of existence. As we ponder the mysteries of the quantum vacuum, one thing becomes clear. The universe is far more dynamic and interconnected than we ever imagined. What we once thought of as empty space is actually a vibrant, energetic field filled with possibilities and potential. It's a reminder that even in the void, there's no such thing as true emptiness, only an infinite dance of energy and matter, constantly shaping the fabric of reality. And as we continue to explore these quantum anomalies, we'll uncover even more ways in which the universe defies our expectations, revealing a cosmos that's far stranger and more beautiful than we ever thought possible. Now let's tackle one of the greatest challenges in modern physics, the quest to unite quantum mechanics with gravity. Think of it like trying to mix oil and water. No matter how hard you stir, the two just don't blend. In the same way, quantum mechanics, which governs the behavior of the very small, and gravity, which shapes the cosmos on the largest scale, seem to operate by entirely different rules. For decades, scientists have been searching for a way to bridge this gap, but the puzzle remains unsolved. Could this be the key to unlocking a deeper understanding of the universe? At the heart of the problem is the fact that quantum mechanics and general relativity, Einstein's theory of gravity, are like two languages that don't translate well. Quantum mechanics describes a world of probabilities where particles exist in multiple states at once and can teleport or tunnel through barriers. Gravity, on the other hand, paints a picture of a smooth, curved space-time, where massive objects like planets and stars warp the fabric of reality. When you try to apply quantum rules to gravity or vice versa, the math breaks down. It's as if the universe itself is telling us we're missing a crucial piece of the puzzle. So, how do we solve this cosmic riddle? One promising approach is string theory, which suggests that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings exist in multiple dimensions, and their vibrations give rise to everything we see: particles, forces, even space and time. String theory offers a way to unify quantum mechanics and gravity by treating them as different aspects of the same underlying reality. It's like discovering that oil and water aren't so different after all. They're just two sides of the same coin. Another intriguing idea is loop quantum gravity, which proposes that space-time itself is made up of tiny, discrete loops. Instead of a smooth, continuous fabric, space-time is more like a woven tapestry, with each thread representing a quantum of space. This theory suggests that gravity emerges from the interactions of these loops, offering a new way to reconcile it with quantum mechanics. It's a radical reimagining of the universe, one that challenges our most basic assumptions about how reality works. But here's the thing: both string theory and loop quantum gravity are still works in progress. While they offer tantalizing glimpses of a unified theory, neither has been proven experimentally yet. The search for quantum gravity is one of the most ambitious and exciting endeavors in science, pushing the boundaries of what we know and challenging us to think in entirely new ways. What if solving this puzzle could reveal a reality that's even stranger and more interconnected than we've ever imagined? What if the key to understanding the cosmos lies in the spaces between the theories we already have? As we grapple with these questions, one thing becomes clear: the quest for quantum gravity isn't just about finding a new equation or theory. It's about uncovering a deeper truth about the universe, one that might reshape our understanding of space, time, and existence itself. And as we continue to explore these quantum anomalies, we'll uncover even more ways in which the universe defies our expectations, inviting us to peer into the unknown and discover what lies beyond the limits of our current knowledge. The journey is far from over, and the next revelation might be just around the corner. Let's step into a realm where time itself becomes unpredictable, almost dreamlike. In the quantum world, time doesn't flow in the steady, linear way we're used to. Instead, it behaves more like a clock in a dream, sometimes speeding up, sometimes slowing down, and occasionally even skipping beats. This erratic behavior is one of the most fascinating and perplexing aspects of quantum mechanics, and it challenges everything we think we know about the nature of time. To understand this, let's start with a simple analogy. Imagine you're in a dream and you glance at a clock. The hands might jump forward suddenly or spin backward, defying the orderly progression of seconds, minutes, and hours. In the quantum world, time operates in a similarly strange and unpredictable way. Particles don't experience time as a smooth, continuous flow. Instead, their interactions can seem to happen out of order, with events appearing to influence each other in ways that defy our everyday understanding of cause and effect. This phenomenon is often referred to as quantum time, and it's deeply tied to the probabilistic nature of quantum mechanics. In the classical world, we assume that cause always precedes effect, that the past influences the future, but not the other way around. But in the quantum realm, this isn't always the case. Experiments have shown that particles can exhibit behaviors that seem to blur the line between past and future, as if time itself is more fluid and malleable than we ever imagined. One striking example of this is the delayed choice experiment, where the decision of how to measure a particle can seemingly affect its behavior in the past. It's as if the universe is playing a cosmic game of cards, where the rules of the game aren't fixed until after the cards have been dealt. This challenges our classical notion of causality, suggesting that time might not be as straightforward as we think. Could it be that the quantum world operates on a kind of time soup, where past, present, and future are all intertwined in ways we can't fully grasp? The implications of quantum time are profound, especially when it comes to our understanding of reality. If time isn't a fixed linear progression, what does that say about the nature of existence? Could it be that the universe itself is a kind of quantum tapestry, where every moment is connected to every other moment, regardless of when or where they occur? This idea takes us to the edge of what we know, challenging us to rethink not just physics, but the very fabric of time itself. And here's where things get even more intriguing. If time behaves differently at the quantum level, could it also influence the larger classical world we experience? Some scientists speculate that quantum time might hold the key to understanding phenomena like black holes, where the laws of time and space break down entirely. Others suggest it could offer clues to the nature of consciousness, perception, and even free will. Could our experience of time, the ticking of the clock, the passage of days, be shaped by the quantum processes happening all around us? As we grapple with these questions, one thing becomes clear: quantum time isn't just a quirk of physics. It's a window into a deeper, more interconnected reality, one where the rules of time and causality might be far more flexible than we ever imagined. And as we continue to explore these quantum anomalies, we'll uncover even more ways in which the universe defies our expectations, reshaping our understanding of what's possible. The next anomaly we'll examine takes this strangeness even further, revealing a universe where the very concept of time might need to be rewritten entirely. Stay tuned, because the quantum journey is about to get even more fascinating. Now, let's take a bold step into one of the most speculative and fascinating areas of quantum mechanics, the idea of quantum consciousness. What if your mind, your thoughts, your very sense of self were not just products of neurons firing in your brain, but also deeply connected to the strange, unpredictable world of quantum physics? Imagine your brain not as a classical computer processing information in clear, binary steps, but as a quantum computer where thoughts and decisions exist in a superposition of possibilities, waiting for observation to collapse them into a single reality. This idea isn't just science fiction, it's a serious, if controversial, theory that suggests consciousness itself might be a quantum phenomenon. To understand this, let's use a metaphor. Think of your mind as a quantum computer. In a classical computer, information is processed in bits, which can be either zeros or ones. But in a quantum computer, qubits can exist in multiple states at once, thanks to superposition. Similarly, your thoughts might not be fixed linear processes, but rather a dynamic interplay of possibilities, with your consciousness acting as the observer that collapses these possibilities into a single, coherent experience. This theory, often referred to as the ORCH or Model Orchestrated Objective Reduction, proposes that tiny structures inside your brain's neurons, called microtubules, could be the site of quantum activity. These microtubules might act like quantum processors, allowing your brain to perform complex calculations and generate consciousness through quantum interactions. It's an audacious idea, one that bridges the gap between the microscopic world of quantum physics and the deeply personal experience of being aware. But what does this mean for free will? If our thoughts and decisions are influenced by quantum processes, does that mean our choices are inherently unpredictable, shaped by the probabilistic nature of the quantum world? Some scientists argue that quantum consciousness could provide a scientific basis for free will, suggesting that the randomness of quantum mechanics allows for genuine choice rather than a predetermined chain of cause and effect. It's as if the universe is giving us a cosmic wild card, a chance to shape our own reality through the power of observation and decision. Of course, this theory is far from proven. Critics argue that the brain is too warm and noisy for delicate quantum processes to occur without being disrupted. But even if quantum consciousness remains speculative, it raises profound questions about the nature of thought, perception, and the self. Could our minds be more than just biochemical machines? Could they be tapping into the quantum fabric of the universe itself, weaving our experiences from the threads of possibility? The implications of this idea are staggering. If consciousness is indeed a quantum phenomenon, it could reshape our understanding of everything from memory and perception to creativity and emotion. It might even hint at a deeper connection between mind and matter, suggesting that the universe itself is in some way conscious. This isn't just about understanding the brain, it's about exploring the very essence of what it means to be alive, to think, to feel, to exist. As we ponder these questions, one thing becomes clear. The intersection of quantum mechanics and consciousness is a frontier as vast and mysterious as the cosmos itself. It challenges us to rethink not just how the brain works, but how we fit into the grand tapestry of the universe. And as we continue to explore these quantum anomalies, we'll uncover even more ways in which the universe defies our expectations, inviting us to peer into the unknown and discover what lies beyond the limits of our current understanding. The journey is far from over, and the next revelation might be closer than we think. Now, let's venture into one of the most provocative ideas in quantum mechanics: quantum immortality. Imagine you're playing a video game and your character is on the verge of dying. But instead of the game ending, you suddenly find yourself respawning in a new level, alive and ready to keep going. In the quantum world, some theorists suggest that something eerily similar might happen with consciousness. According to the concept of quantum immortality, your awareness could persist across parallel universes, always finding a reality where you survive, no matter how unlikely it seems. This idea stems from the many worlds interpretation of quantum mechanics, which we explored earlier. Remember how every quantum event creates branching universes, each representing a different outcome. Quantum immortality takes this a step further, proposing that your consciousness might always follow the path where you continue to exist. Even in a situation where death seems inevitable, like a catastrophic accident or a fatal illness, there's always a universe where you somehow survive, and your awareness seamlessly shifts to that reality. It's as if the universe is constantly giving you a save point, ensuring your consciousness never truly ends. But what does this mean for our understanding of life and death? If consciousness can persist across parallel realities, does that mean death is an illusion? Could it be that, from your perspective, you're always alive, even as other versions of you in other universes meet their end? This idea challenges our deepest assumptions about mortality. suggesting that the end of life as we know it might not be as final as we think. Of course, quantum immortality is a highly speculative concept, and it raises as many questions as it answers. For one, how would this work on a practical level? If you're always shifting to a reality where you survive, wouldn't the world around you start to feel increasingly improbable? Imagine narrowly escaping disaster after disaster, living in a reality that seems to bend over backward to keep you alive. It's a fascinating and slightly unsettling thought experiment that pushes the boundaries of what we consider possible. What's even more intriguing is how this idea intersects with our understanding of consciousness itself. If your awareness can persist across parallel universes, does that mean consciousness is a fundamental feature of the universe rather than just a byproduct of the brain? Could it be that the self is more than just a collection of neurons, but something that transcends individual realities? These questions blur the line between science and philosophy, inviting us to rethink not just the nature of life and death, but the very essence of who we are. As we ponder the implications of quantum immortality, one thing becomes clear: the quantum world is a place where the rules of reality are far stranger than we ever imagined. It challenges us to question not just how the universe works, but how we fit into it, and whether the boundaries of life and death might be more fluid than we've ever dared to believe. And as we continue to explore these quantum anomalies, the mysteries only grow deeper, inviting us to peer into the unknown and discover what lies beyond the limits of our current understanding. The next anomaly we'll examine takes this strangeness even further, revealing a universe where the very concept of existence might need to be rewritten entirely. Stay with us because the quantum journey is about to get even more fascinating. Let's take a step into a field that merges the strange world of quantum mechanics with the intricate dance of life itself, quantum biology. Imagine a bird soaring across the sky, navigating thousands of miles with pinpoint accuracy. How does it know where to go? Some scientists believe the answer might lie in the quantum realm. It turns out the natural world might be tapping into quantum effects in ways we're only beginning to understand. From the way plants photosynthesize to how our own cells function, quantum mechanics could be playing a hidden role in the very fabric of life. One of the most fascinating examples of this is the idea that birds might use quantum entanglement to navigate. Picture this: as a bird flies, tiny particles in its retina, called cryptochromes, interact with Earth's magnetic field. These particles become entangled, creating a kind of quantum compass that helps the bird sense direction. It's as if the bird is reading a map written in the language of quantum physics, using the spooky connection between particles to guide its journey. This isn't just a wild theory. Experiments have shown that cryptochromes do respond to magnetic fields, and quantum entanglement might be the key to explaining how. But birds aren't the only ones benefiting from quantum effects. Take photosynthesis, for example. When plants absorb sunlight, the energy needs to travel through a network of molecules to reach the reaction center where it's converted into fuel. Classical physics would predict that this energy would bounce around randomly, losing efficiency along the way, but somehow plants achieve near-perfect efficiency. Scientists believe that quantum coherence, the same phenomenon that allows particles to exist in multiple states at once, might be at play. It's as if the energy is taking every possible path at once, finding the quickest route to its destination. This discovery could revolutionize how we think about energy transfer, not just in nature but in technology as well. And then there's the human body. Recent research suggests that quantum effects might even be at work in our own cells. Enzymes, the molecular machines that drive countless biological processes, seem to use quantum tunneling to speed up chemical reactions. This allows them to break down molecules or build new ones with incredible precision, far faster than classical chemistry would allow. It's almost as if life itself has evolved to harness the strange rules of the quantum world, using them to its advantage. What does this mean for evolution? If quantum effects are woven into the very processes that sustain life, it could change how we think about natural selection. Evolution might not just be about random mutations and survival of the fittest, it could also involve optimizing quantum efficiencies. This idea blurs the line between biology and physics, suggesting that life might be more deeply connected to the fundamental laws of the universe than we ever imagined. And the implications for medicine are equally profound. If we can understand and harness these quantum processes, we might unlock new ways to treat diseases, design drugs, or even repair damaged tissues. Imagine therapies that use quantum coherence to target cancer cells with pinpoint accuracy, or enzymes engineered to perform specific tasks with quantum precision. The possibilities are as exciting as they are mind-bending. So, what if life itself is a quantum phenomenon? What if the same principles that allow particles to exist in multiple states at once, or to communicate instantaneously across vast distances, are also the building blocks of life? These questions take us to the edge of what we know, inviting us to explore a universe where the boundaries between physics, biology, and consciousness might not be as clear as we think. And as we continue to unravel these mysteries, we might just discover that the quantum world isn't just a part of life, it might be the very essence of it. Now let's dive into a concept that feels almost poetic in its complexity: quantum chaos. Imagine a butterfly perched on a leaf, its delicate wings fluttering ever so slightly. In the classical world, this tiny motion might seem insignificant, but in the world of weather systems, it's the spark that could ignite a hurricane halfway across the globe. This idea, often called the butterfly effect, is a hallmark of chaos theory, a field that studies how small changes can lead to wildly unpredictable outcomes. But what happens when we bring this concept into the quantum realm? The results are even more astonishing. In quantum systems, chaos takes on a whole new dimension. Here, even the tiniest fluctuations like the spin of a single electron or the position of a photon can cascade into dramatic, unpredictable effects. Think of it like this. In the quantum world, particles exist in a delicate balance of probabilities, their behaviors governed by waves of uncertainty. A slight nudge to one particle might ripple through the system, causing a chain reaction that alters the entire state of the system in ways we can't foresee. It's as if the quantum universe is a house of cards, where even the gentlest breeze can bring the entire structure tumbling down. This unpredictability has profound implications for our ability to predict and control quantum systems. In the classical world, we often assume that if we know the starting conditions of a system, we can predict its future behavior. But in the quantum realm, this assumption breaks down. The inherent uncertainty of particles means that even the most precise measurements can't guarantee accurate predictions. It's like trying to forecast the weather in a world where the atmosphere is constantly reshuffling itself, defying all attempts at modeling. But here's where things get even more intriguing. Quantum chaos isn't just a limitation, it might be a fundamental feature of reality itself. Some scientists suggest that chaos could be the driving force behind the complexity and diversity of the universe. Without it, everything might fall into a static, predictable pattern, leaving no room for the dynamic, ever-changing world we live in. Chaos, in this sense, might be what gives the universe its richness and unpredictability, making it a place of endless possibilities rather than a clockwork machine. This idea challenges our classical notions of order and control, suggesting that unpredictability isn't a flaw in the system, it's the system. It's as if the universe thrives on a delicate balance between order and chaos, with quantum mechanics providing the perfect playground for this interplay. And while this might make it harder for us to predict outcomes, it also opens the door to a more creative, dynamic understanding of reality. So, what does this mean for us? If chaos is woven into the fabric of the quantum world, could it also shape the larger, classical world we experience? Might chaos be the hidden force behind everything from the formation of galaxies to the flicker of a candle flame? These questions take us to the edge of what we know, inviting us to see unpredictability not as a problem to be solved, but as a fundamental feature of existence. As we ponder the role of chaos in the universe, one thing becomes clear. The quantum world is a place where the rules are not just strange, they're beautifully, unpredictably complex. It's a reminder that reality is far more dynamic and interconnected than we ever imagined, and that sometimes it's the very unpredictability of the universe that makes it so extraordinary. And as we continue to explore these quantum anomalies, we'll uncover even more ways in which the cosmos defies our expectations, reshaping our understanding of what's possible. The journey is far from over, and the next revelation might be just around the corner. Now, let's explore one of the most mind-bending ideas in modern physics, the notion that the universe itself might be a hologram. Picture this: you're sitting in a movie theater watching a 3D film. The images on the screen appear to have depth, texture, and movement. They feel real, even though you know they're just light projected onto a flat surface. Now imagine that the entire universe works in a similar way. What if everything we see, feel, and experience is just a projection, a hologram encoded on a distant two-dimensional surface? This is the essence of quantum holography, a theory that suggests reality might not be as three-dimensional as it seems. At its core, quantum holography is rooted in the idea that all the information about the universe, every star, every planet, every atom, could be stored on a boundary like the surface of a sphere. This boundary acts like a cosmic hard drive, encoding the data needed to project the 3D world we experience. It's as if the universe is a giant hologram, with the physical world we perceive being a kind of illusion, a projection of information from a deeper, hidden layer of reality. This idea isn't just a wild thought experiment, it's supported by some of the most advanced theories in physics, including string theory and black hole thermodynamics. So how does this work? Let's break it down. Imagine you're looking at a photograph. From a distance, it appears sharp and detailed. But if you zoom in, you'll see it's made up of tiny pixels, individual points of data that come together to create the image. In the holographic universe, something similar happens. The 3D world we experience is like the photograph, while the 2D surface is like the pixels. Every event, every object, every moment in time could be encoded on this surface, with the information being read and projected into the 3D space we perceive. It's a radical reimagining of reality, one that blurs the line between the physical and the informational. But what does this mean for our understanding of space and time? If the universe is a hologram, then space and time might not be fundamental. They could be emergent properties arising from the way information is encoded and projected. This idea challenges our classical view of a fixed, objective reality, suggesting instead that space and time are like the screen in a movie theater, a surface onto which the universe projects its story. It's as if the fabric of reality itself is woven from information, and what we perceive as the physical world is just one layer of a much deeper, more complex structure. The implications of this theory are staggering. If the universe is a hologram, then everything we see, stars, galaxies, even ourselves, might be part of a grand cosmic illusion. It raises profound questions about the nature of existence. What is real? Is the physical world just a projection of something deeper? And if so, what lies beyond the hologram? These questions take us to the edge of what we know, inviting us to rethink not just physics, but the very nature of reality itself. And here's where things get even more intriguing. If the universe is a hologram, could it also explain some of the strange phenomena we've already explored, like quantum entanglement or the observer effect? Could these anomalies be glimpses of the underlying information layer, where the rules of reality are written in a language we're only beginning to understand? This idea opens up a whole new frontier in science, one where the boundaries between physics, information theory, and philosophy begin to blur. As we grapple with the implications of quantum holography, one thing becomes clear: the universe is far more mysterious and interconnected than we ever imagined. It challenges us to see reality not as a fixed objective thing, but as a dynamic, ever-changing projection of something deeper and more fundamental. And as we continue to explore these quantum anomalies, we'll uncover even more ways in which the cosmos defies our expectations, reshaping our understanding of what's possible. The journey into the quantum world is far from over, and the next revelation might be closer than we think. Now, let's turn our attention to a concept that's as inevitable as it is mysterious: quantum entropy. Picture a sandcastle on the beach, its intricate towers and walls meticulously shaped by hand. Over time, the wind, waves, and heat of the sun work together to erode it grain by grain until it's nothing more than a shapeless mound of sand. This gradual descent into disorder isn't just a poetic image, it's a perfect analogy for entropy, the natural tendency of systems to move from order to chaos. And in the quantum world, entropy plays a role that's just as profound, shaping the very fabric of reality. At its core, entropy is a measure of disorder. In classical physics, it's often associated with the second law of thermodynamics, which states that in any closed system, entropy always increases over time. This is why a cold cup of coffee left on a table will always warm up to room temperature, or why a drop of dye in water will eventually spread out until the liquid is uniformly colored. But in the quantum realm, entropy takes on a more nuanced role. Here, it's not just about the movement of heat or the mixing of substances. It's about the way information itself becomes scrambled, making it harder and harder to track the state of a system as time goes on. To understand this, think of a quantum system as a deck of cards. When the deck is new, it's perfectly ordered, each card is in its place, and you know exactly what to expect. But as you shuffle the deck, the order breaks down, cards become mixed, and predicting their sequence becomes nearly impossible. In the quantum world, this shuffling happens through interactions between particles where their states become increasingly entangled and chaotic. Over time, the system evolves toward a state of maximum entropy, where information is so scrambled that it's effectively lost. But here's where things get truly fascinating. Quantum entropy isn't just a quirk of physics, it's deeply tied to the arrow of time. The idea that time flows in one direction from past to future. In the macroscopic world, we experience time as a steady, irreversible progression. You can't unscramble an egg, unburn a log, or rebuild a sandcastle from scattered grains. This irreversibility is a direct result of entropy, which gives time its directionality. Without entropy, the past and future would be indistinguishable, and the arrow of time would lose its meaning. What's even more intriguing is how quantum entropy might shape the ultimate fate of the universe. Some scientists speculate that entropy could be the key to understanding whether the cosmos will end in a heat death, where all energy is evenly distributed and no work can be done, or whether it might collapse back on itself in a big crunch. These scenarios hinge on how entropy evolves over cosmic timescales and whether the universe can ever escape its inevitable march toward disorder. So, what does this mean for us? If entropy is the driving force behind the arrow of time, could it also hold clues to the nature of existence itself? Could the relentless increase of entropy be the reason we remember the past but not the future, or why we perceive time as flowing in one direction? These questions take us to the edge of what we know, inviting us to see entropy not just as a measure of disorder, but as a fundamental feature of reality, one that shapes everything from the tiniest particles to the vast expanse of the cosmos. As we reflect on the role of entropy in the universe, one thing becomes clear: the quantum world is a place where order and chaos are locked in an eternal dance. It's a reminder that the universe is far more dynamic and interconnected than we ever imagined, and that even the most seemingly mundane phenomena like the crumbling of a sandcastle can hold profound insights into the nature of reality. And as we continue to explore these quantum anomalies, we'll uncover even more ways in which the cosmos defies our expectations, reshaping our understanding of what's possible. The journey into the quantum world is far from over, and the next revelation might be closer than we think. Now, let's step into a world where beauty and order meet the strange rules of quantum mechanics, the world of quantum symmetry. Picture a kaleidoscope, its intricate mirrors reflecting and refracting light to create mesmerizing, perfectly symmetrical patterns. Each twist of the tube produces a new design, yet the underlying symmetry remains constant, a hidden blueprint guiding the chaos. In the quantum realm, symmetry plays a similar role, acting as an invisible framework that shapes the behavior of particles and the structure of the universe itself. But what does this mean for our understanding of reality? In physics, symmetry isn't just about aesthetics, it's a fundamental principle that governs the laws of nature. At its core, symmetry means that something remains unchanged even when you transform it in some way. For example, a circle looks the same no matter how you rotate it. In the quantum world, symmetries are like the hidden rules that dictate how particles interact, how forces are transmitted, and even how the universe evolves over time. These symmetries aren't just mathematical curiosities, they're the scaffolding that holds reality together. One of the most striking examples of symmetry in quantum mechanics is the concept of gauge symmetry. Imagine you're tuning a musical instrument. No matter how you adjust the tuning pegs, the relationship between the strings remains the same. The music stays harmonious. Gauge symmetry works in a similar way, ensuring that the fundamental forces of nature like electromagnetism and the strong nuclear force remain consistent no matter how you tune the equations that describe them. This symmetry is so powerful that it forms the backbone of the standard model of particle physics, the theory that explains how all known particles and forces interact. But symmetry in the quantum world isn't just about consistency, it's also about discovery. When physicists uncover a new symmetry, it often leads to groundbreaking revelations. Take the discovery of antimatter, for example. In the 1920s, physicist Paul Dirac noticed a symmetry in his equations that suggested the existence of particles with the same mass as electrons but opposite charge. At the time, no one had ever observed such a particle, but Dirac's symmetry-based prediction turned out to be correct. The positron, the electron's antimatter counterpart, was discovered just a few years later. This is the power of symmetry. It doesn't just describe the universe, it helps us uncover its hidden secrets. So, what does this mean for the bigger picture? Symmetry isn't just a tool for physicists, it's a window into the deeper structure of reality. Some scientists believe that the symmetries we've discovered so far might be just the tip of the iceberg, hinting at an even grander symmetry that unites all the forces of nature into a single, elegant framework. This idea, often referred to as the theory of everything, is one of the holy grails of modern physics. If such a symmetry exists, it could revolutionize our understanding of the cosmos, revealing a universe that's far more interconnected and harmonious than we ever imagined. And here's where things get even more intriguing. Symmetry doesn't just shape the physical world, it might also hold the key to understanding the very nature of existence. Could the symmetries we observe in particles and forces be reflections of a deeper, more fundamental order? Some theorists suggest that these symmetries might be clues to the ultimate nature of reality, pointing to a universe where everything is interconnected in ways we're only beginning to grasp. It's as if the universe is a grand symphony with symmetry as the score that guides every note. As we reflect on the role of symmetry in the quantum world, one thing becomes clear: the universe is far more elegant and interconnected than we ever imagined. It's a place where beauty and order aren't just abstract concepts, they're the very fabric of reality. And as we continue to explore these quantum anomalies, we'll uncover even more ways in which the cosmos defies our expectations, reshaping our understanding of what's possible. The journey into the quantum world is far from over, and the next revelation might be closer than we think. Now, let's dive into a concept that reshapes how we think about particles and the very fabric of reality: quantum fields. Imagine standing by the edge of a calm lake on a windless day. The surface is smooth, almost like glass, but then you toss a pebble into the water. Ripples spread outward, forming waves that move across the lake. These waves aren't the water itself, they're disturbances, energy moving through the water. In the quantum world, particles like electrons or photons behave in a similar way. They're not solid, static objects, but rather excitations, ripples in an underlying field that permeates all of space. Think of these fields as invisible, all-encompassing lakes that stretch across the universe. Just as the surface of a lake can have waves, these quantum fields can have ripples, and those ripples are what we perceive as particles. An electron, for example, isn't a tiny ball bouncing around. It's a localized disturbance in the electron field. A photon, a ripple in the electromagnetic field. Even the Higgs boson, the particle that gives other particles mass, is an excitation of the Higgs field. In this view, particles aren't the fundamental building blocks of the universe, fields are. This idea turns our classical understanding of matter on its head. Instead of thinking of particles as discrete, independent entities, quantum field theory suggests that everything is connected through these fields. It's like realizing that every wave on the lake is part of the same body of water, each one arising from the same underlying medium. This interconnectedness is one of the most profound insights in modern physics, revealing a universe that's far more unified than we ever imagined. But what does this mean for the nature of reality? If particles are just excitations of fields, then what we perceive as solid, tangible matter might be more like energy patterns dancing on the surface of an invisible ocean. It's as if the universe is a vast, dynamic tapestry woven from the threads of these fields, with particles as the knots and ripples that give it texture. This perspective doesn't just change how we see particles, it changes how we see everything. Could it be that fields, not particles, are the true building blocks of reality? The implications of this idea are staggering. For one, it suggests that the universe is far more interconnected than we realize. If every particle is a ripple in a field, then every interaction between particles is an interaction between fields. This interconnectedness might even hold the key to understanding phenomena like entanglement, where particles separated by vast distances seem to communicate instantaneously. Could it be that entanglement isn't about particles talking to each other, but about the fields they're part of being fundamentally linked? And here's where things get even more intriguing. If fields are the foundation of reality, what does that say about the nature of space and time? Some physicists speculate that fields might not just exist within space and time, they might define them. In this view, space and time could emerge from the interactions of fields, like the surface of a lake emerging from the movement of water molecules. This idea takes us to the edge of what we know, challenging us to rethink not just the nature of matter, but the very fabric of existence. As we reflect on the role of quantum fields in shaping the universe, one thing becomes clear: the cosmos is far more dynamic and interconnected than we ever imagined. It's a place where particles are not isolated objects but ripples in a vast, invisible ocean, where every interaction is part of a grand cosmic dance. And as we continue to explore these quantum anomalies, we'll uncover even more ways in which the universe defies our expectations, reshaping our understanding of what's possible. The journey into the quantum world is far from over, and the next revelation might be closer than we think. Now, let's step into a phenomenon that feels like magic: quantum non-locality. Imagine two dancers on opposite ends of a stage moving in flawless harmony. No matter how far apart they are, every step, every gesture, every spin is perfectly synchronized, as if they're connected by an invisible thread. In the quantum world, particles can behave in a strikingly similar way. They can influence each other instantaneously, no matter the distance between them, as if they're dancing to the same cosmic rhythm. This isn't just a poetic metaphor, it's a real, measurable phenomenon that challenges our understanding of space, time, and the very nature of connection. At the heart of quantum non-locality is the idea that particles can be entangled, sharing a bond that defies the limits of space and time. When two particles become entangled, their properties, like spin or polarization, are linked in such a way that measuring one instantly determines the state of the other, even if they're light years apart. It's as if the universe has a hidden network, a kind of quantum internet that allows particles to communicate faster than the speed of light. This instantaneous connection, known as spooky action at a distance by Einstein, has been confirmed through countless experiments, leaving scientists both amazed and perplexed. But what does this mean for our understanding of causality, the idea that cause must always precede effect? In the classical world, we assume that nothing can travel faster than light, and that events unfold in a clear, linear sequence. But quantum non-locality throws a wrench into this tidy picture. If particles can influence each other instantaneously, does that mean causality is an illusion? Could it be that the universe operates on a deeper level where past, present, and future are more fluid than we think? These questions take us to the edge of what we know, challenging us to rethink not just physics, but the very fabric of reality. The implications of non-locality extend far beyond the realm of particle physics. Imagine a future where we could harness this phenomenon for communication. Picture a world where information travels instantaneously without the delays imposed by distance. This isn't just science fiction. Scientists are already exploring how quantum entanglement could revolutionize technologies like quantum computing and secure communication. By tapping into the non-local connections between particles, we might unlock entirely new ways to process and transmit information, transforming how we connect with each other and the world around us. But here's where things get even more intriguing. If particles can communicate instantaneously, what does that say about the nature of space itself? Could it be that space is not the vast, empty void we imagine, but a dynamic, interconnected web where distance is an illusion? Some theorists suggest that non-locality might be a clue to a deeper reality, one where the universe is fundamentally unified, and the boundaries we perceive are just a projection of our limited perspective. It's as if the universe is a giant puzzle, and non-locality is a piece that doesn't quite fit yet. As we grapple with the mysteries of quantum non-locality, one thing becomes clear: the universe is far more interconnected and mysterious than we ever imagined. It challenges us to see reality not as a collection of separate objects, but as a dynamic, entangled whole where every particle, every force, every moment is deeply linked. And as we continue to explore these quantum anomalies, the mysteries only grow deeper, inviting us to peer into the unknown and discover what lies beyond the limits of our current understanding. The journey into the quantum world is far from over, and the next revelation might be closer than we think. Now, let's step into a groundbreaking idea that redefines how we see the universe: quantum information. Imagine a vast cosmic library, its shelves stretching endlessly in every direction. Each book on these shelves isn't filled with words or pictures. It contains the fundamental data that makes up reality itself. The position of every star, the spin of every electron, even the thoughts in your mind, all of it is encoded in this infinite repository. This isn't just a whimsical metaphor, it's a radical shift in how physicists understand the fabric of existence. In the quantum world, information isn't just something we process, it's the very essence of reality. At its core, quantum information is the idea that everything in the universe can be boiled down to bits of data. Particles, forces, even space and time, they're all expressions of information. Think of it like this: if the universe were a computer, information would be the code running the program. Every interaction, every event, every moment in time is a computation, a transformation of information from one state to another. This perspective doesn't just change how we think about physics, it changes how we think about everything. Could it be that the universe isn't made of matter and energy, but of information itself? This idea has profound implications for computing. In the classical world, computers process information in binary zeros and ones. But in the quantum realm, information exists in qubits, which can be 0, 1, or both at the same time thanks to superposition. This allows quantum computers to perform calculations at mind-boggling speeds, solving problems that would take classical computers millions of years. It's like upgrading from a candle to a laser beam. The difference isn't just incremental, it's revolutionary. Quantum computing could transform fields like cryptography, medicine, and artificial intelligence, opening doors to discoveries we can't yet imagine. But quantum information isn't just about technology, it's also reshaping our understanding of existence. If information is the fundamental building block of reality, then what we perceive as the physical world might be a kind of projection, a hologram generated by the underlying data. It's as if the universe is constantly computing itself, using information as the code to render everything from galaxies to grains of sand. This idea blurs the line between the physical and the informational, suggesting that reality might be more like a simulation than a fixed, objective thing. And here's where things get even more intriguing. If information shapes reality, could we, as observers, play a role in that process? Could the act of observing or measuring something like in the Double-Slit Experiment be a way of reading the cosmic library, collapsing quantum possibilities into definite realities? This idea takes us back to the heart of quantum mechanics, where the line between observer and observed becomes increasingly blurred. It challenges us to see ourselves not just as passive witnesses to the universe, but as active participants in its unfolding story. So, what does this mean for the bigger picture? Quantum information isn't just a tool for physicists, it's a window into the deeper structure of reality. Some scientists believe that understanding information could be the key to unlocking the ultimate nature of the cosmos. Could it be that the universe is a kind of quantum computer running the program of existence, or that information is the thread that connects everything from the smallest particles to the vast expanse of space? These questions take us to the edge of what we know, inviting us to explore a universe that's far more interconnected and far stranger than we ever imagined. As we reflect on the role of information in shaping reality, one thing becomes clear: the universe is far more dynamic and mysterious than we ever thought. It's a place where the boundaries between the physical and the informational are fluid, where every particle, every force, every moment is part of a grand cosmic computation. And as we continue to explore these quantum anomalies, the mysteries only grow deeper, reshaping our understanding of what's possible. The next anomaly we'll examine takes this interconnectedness even further, revealing a universe where the very fabric of reality might be woven from the threads of information itself. Stay with us, because the quantum journey is about to get even more fascinating. Imagine a cosmic vacuum cleaner so powerful that it doesn't just suck up dust, it warps the very fabric of space and time, creating a region where the laws of physics as we know them break down. This is the essence of a black hole, one of the most mysterious and awe-inspiring phenomena in the universe. But here's the twist: black holes aren't just cosmic oddities, they're also quantum enigmas, challenging our understanding of reality in ways that even Einstein couldn't fully grasp. At the heart of a black hole lies the singularity, a point where gravity becomes infinitely strong and space-time curves so sharply that it essentially tears. Picture a rubber sheet stretched tight with a bowling ball placed in the center. The ball creates a deep, funnel-shaped dip in the sheet. Now imagine that dip becoming infinitely deep. That's what happens at the singularity. But here's where quantum mechanics throws a wrench into the works. According to quantum theory, particles and energy can't just vanish into nothingness. So what happens to all the matter and information that gets sucked into a black hole? Does it disappear forever, or is it somehow preserved? This question has sparked one of the greatest debates in modern physics. The clash between quantum mechanics and black holes is best illustrated by something called the information paradox. In the quantum world, information like the spin of an electron or the charge of a proton is never truly lost. It might get scrambled or transformed, but it's always conserved. But black holes seem to defy this rule. When matter falls into a black hole, it's crushed into the singularity, leaving no trace of its original state. This creates a paradox. If quantum mechanics says information can't be destroyed, but black holes seem to erase it, which one is right? One possible solution to this puzzle comes from the idea of Hawking radiation, named after physicist Stephen Hawking. Black holes aren't entirely black. They emit tiny amounts of radiation due to quantum effects near their event horizons, the boundaries beyond which nothing can escape. Over time, this radiation causes black holes to lose mass and eventually evaporate. But here's the catch: if a black hole evaporates, what happens to all the information it swallowed? Some scientists believe the information might be encoded in the radiation itself, like a cosmic message in a bottle. Others suggest that black holes might not be the end of the story at all. They could be gateways to entirely new realities. This idea takes us to the edge of what we know, hinting at a universe far stranger and more interconnected than we ever imagined. Could black holes be portals to other dimensions or parallel universes? Might they hold the key to unifying quantum mechanics and gravity, two theories that have stubbornly resisted reconciliation? These questions aren't just academic. They could reshape our understanding of the cosmos, revealing a reality where the boundaries between space, time, and existence itself are far more fluid than we think. As we peer into the heart of a black hole, we're not just exploring the limits of physics, we're confronting the limits of our own understanding. It's a reminder that the universe is full of mysteries waiting to be uncovered, and that even the darkest corners of space might hold the brightest secrets. And as we continue this journey into the quantum realm, the next anomaly we'll explore might just reveal a universe where even black holes are just the beginning. Now, let's step into one of the most elusive mysteries of the cosmos: dark matter. Imagine walking through a crowded room, feeling the brush of unseen hands guiding you, shaping your path, yet never knowing who or what is doing the pushing. Dark matter is like that invisible hand, an unseen force that shapes the universe on a grand scale, influencing the motion of galaxies, the bending of light, and the very structure of the cosmos. And while we can't see it or touch it directly, its presence is undeniable. But here's the twist: what if dark matter isn't just a shadowy, classical substance? What if it's deeply tied to the strange, unpredictable world of quantum mechanics? At its core, dark matter is the name we give to the mysterious substance that makes up about 85% of the universe's mass. We know it's there because of its gravitational effects. Galaxies spin faster than they should, and light bends in ways that can't be explained by the visible matter we see. But despite decades of searching, we've never directly detected a single particle of dark matter. This has led scientists to wonder, could dark matter be a quantum phenomenon governed by the same bizarre rules that dictate the behavior of particles like electrons and photons? One intriguing possibility is that dark matter particles are quantum in nature, existing in states that are fundamentally different from the particles we're familiar with. Picture this: while ordinary matter is like a well-behaved orchestra playing predictable notes and rhythms, dark matter might be more like a jazz ensemble, improvising in ways that defy our classical expectations. These particles could be governed by quantum fields that interact so weakly with ordinary matter that they're nearly impossible to detect. It's as if dark matter is a ghostly whisper in the quantum symphony, playing its part but remaining just out of reach. But what if dark matter isn't just a single type of particle? Some theories suggest it could be a complex quantum system, made up of multiple components that interact in ways we don't yet understand. Imagine a cosmic dance where dark matter particles are constantly shifting between states, creating a dynamic, ever-changing fabric that underlies the universe. This idea challenges our classical view of dark matter as a static, invisible substance, suggesting instead that it might be a vibrant, quantum-driven force. The implications of this idea are profound, especially for cosmology. If dark matter is a quantum phenomenon, it could reshape our understanding of how the universe evolved. For instance, quantum fluctuations in the early universe might have seeded the distribution of dark matter, creating the cosmic web of galaxies we see today. It's as if the invisible hand that shapes the universe was guided by the same quantum rules that govern particles at the smallest scales. This connection between the quantum and the cosmic could be the key to unlocking some of the deepest mysteries of existence. And here's where things get even more fascinating. If dark matter is indeed a quantum phenomenon, it might also hold clues to the unification of physics. Could it bridge the gap between quantum mechanics and gravity, two theories that have stubbornly resisted reconciliation? Some scientists speculate that dark matter might interact with gravity in ways we've yet to discover, offering a new perspective on how the universe works at its most fundamental level. This idea takes us to the edge of what we know, inviting us to rethink not just dark matter, but the very fabric of reality. As we explore the quantum nature of dark matter, one thing becomes clear: the universe is far more interconnected and mysterious than we ever imagined. It challenges us to see the cosmos not as a collection of separate phenomena, but as a unified whole where the smallest particles and the largest structures are deeply intertwined. And as we continue to unravel these quantum anomalies, the mysteries only grow deeper, reshaping our understanding of what's possible. The next anomaly we'll examine takes this interconnectedness even further, revealing a universe where the boundaries between the quantum and the cosmic might not be as clear as we think. Stay with us because the quantum journey is about to get even more fascinating. let's dive into one of the most profound mysteries of the cosmos, dark energy. Picture the universe as a balloon slowly inflating over billions of years. Now, imagine an unseen hand pressing against the rubber, causing it to stretch faster and faster. That's dark energy in action, an invisible force that's accelerating the expansion of the universe. But here's the twist. What if this mysterious force isn't just a classical phenomenon? What if it's deeply rooted in the strange, unpredictable world of quantum mechanics? Dark energy makes up about 68% of the universe, and yet we know almost nothing about it. We see its effects: galaxies drifting apart at ever-increasing speeds, the fabric of space itself stretching. But its origin remains a mystery. One intriguing possibility is that dark energy is a quantum effect arising from the same bizarre rules that govern particles at the smallest scales. Think of the quantum vacuum we explored earlier, where particles flicker in and out of existence. Could the energy of this vacuum be the source of dark energy, pushing the universe apart like an invisible cosmic engine? This idea isn't as far-fetched as it sounds. Quantum field theory predicts that empty space isn't truly empty, it's a seething cauldron of energy, with particles and antiparticles constantly popping into existence and annihilating each other. This zero-point energy could, in theory, exert a kind of pressure on the fabric of space-time, driving the universe's expansion. The problem is, when scientists try to calculate how much energy this vacuum should produce, the numbers are staggeringly large, far larger than what we observe in the cosmos. This mismatch, known as the cosmological constant problem, is one of the biggest unsolved puzzles in physics. But what if the solution lies in a deeper understanding of quantum mechanics? Some theorists suggest that dark energy might not be a single, uniform force, but a dynamic, quantum-driven phenomenon that changes over time. Imagine dark energy as a patchwork quilt, with different regions of the universe expanding at different rates, influenced by quantum fluctuations. This idea challenges the classical view of dark energy as a static, unchanging force, suggesting instead that it might be a vibrant, ever-evolving part of the cosmos. The implications of this are staggering. If dark energy is a quantum phenomenon, it could reshape our understanding of the universe's fate. Will the expansion continue forever, eventually tearing galaxies apart in a big rip? Or could dark energy evolve in ways that slow or even reverse the expansion, leading to a big crunch? These questions aren't just academic. They could determine the ultimate destiny of the cosmos. And here's where things get even more intriguing. If dark energy is tied to quantum mechanics, it might also hold the key to unifying the fundamental forces of nature. Could it bridge the gap between quantum physics and gravity, offering a new perspective on how the universe works at its most fundamental level? This idea takes us to the edge of what we know, inviting us to rethink not just dark energy, but the very rules of physics. As we explore the quantum nature of dark energy, one thing becomes clear: the universe is far more dynamic and interconnected than we ever imagined. It challenges us to see the cosmos not as a collection of separate phenomena, but as a unified whole where the smallest particles and the largest structures are deeply intertwined. And as we continue to unravel these quantum anomalies, the mysteries only grow deeper, reshaping our understanding of what's possible. The next anomaly we'll examine takes this interconnectedness even further, revealing a universe where the boundaries between the quantum and the cosmic might not be as clear as we think. Stay with us because the quantum journey is about to get even more fascinating. Now, let's take a journey into one of the most tantalizing possibilities in physics: quantum time travel. Imagine watching a movie where the scenes play in reverse. Characters walk backward, spilled coffee leaps back into its cup, and shattered glass reassembles itself into a pristine window. In the quantum world, something eerily similar might be possible. While time travel remains firmly in the realm of science fiction for our everyday lives, quantum mechanics suggests that at the smallest scales, the arrow of time might not be as rigid as we think. At the heart of this idea is the concept of quantum reversibility. In the classical world, time flows in one direction forward. Eggs break, but they don't unbreak. But in the quantum realm, the rules are different. Particles don't follow a strict timeline. Instead, their behavior is governed by probabilities and wave functions that can, in theory, evolve backward as easily as forward. It's as if the universe has a built-in rewind button, allowing particles to undo their actions under certain conditions. This doesn't mean we can hop into a time machine and visit the dinosaurs, but it does hint at a universe where time might be more flexible than we've ever imagined. One of the most intriguing mechanisms for quantum time travel involves something called closed time-like curves. Picture a loop in space-time, like a cosmic Möbius strip where the end connects back to the beginning. If a particle were to follow such a path, it could theoretically travel back in time, returning to a point in its own past. This idea isn't just a thought experiment. It's rooted in the equations of general relativity, which describe how space-time can bend and twist under extreme conditions. When combined with quantum mechanics, these curves suggest that time travel might not be impossible, just incredibly difficult and limited to the quantum scale. But what does this mean for causality, the idea that cause must always precede effect? If particles can travel back in time, even in theory, does that mean the future can influence the past? Imagine throwing a ball and watching it fly backward into your hand before you've even thrown it. It's a mind-bending scenario that challenges our deepest intuitions about how the universe works. Some scientists argue that quantum time travel could create paradoxes, like the famous grandfather paradox, where traveling back in time to prevent your own birth would make your existence impossible. But others suggest that quantum mechanics might find a way to resolve these paradoxes, perhaps by allowing multiple timelines or parallel universes to coexist. And here's where things get even more fascinating. If time travel is possible on a quantum level, could it also have implications for free will? If the future can influence the past, are our choices truly our own, or are they predetermined by events that haven't happened yet? These questions take us to the edge of what we know, blurring the line between physics and philosophy, and inviting us to rethink not just time, but the very nature of existence. While quantum time travel remains speculative, it's a reminder that the universe is far stranger and more interconnected than we've ever imagined. It challenges us to see time not as a rigid line, but as a dynamic, fluid dimension, full of possibilities we're only beginning to explore. And as we continue to unravel these mysteries, the next anomaly we'll examine might just reveal a universe where time itself is a quantum illusion, and the past, present, and future are all part of the same cosmic dance. Stay with us because the quantum journey is about to get even more fascinating. Now, let's imagine a future where machines don't just think, they think in quantum. Picture an artificial intelligence that doesn't process information in rigid ones and zeros, but instead navigates a world of probabilities where every decision exists in a superposition of possibilities until the moment of action. This isn't just a sci-fi fantasy, it's a tantalizing possibility at the intersection of quantum mechanics and artificial intelligence. What if the next leap in AI isn't about faster processors or bigger datasets, but about harnessing the strange, unpredictable rules of the quantum world? At its core, quantum AI is about reimagining how machines process information. Today's computers rely on classical bits, which can be either a 0 or a 1. But quantum computers use qubits, which can exist in both states simultaneously, thanks to superposition. Imagine an AI that doesn't just evaluate options one at a time, but explores every possible path at once, like a chess player who can see every move and countermove in an instant. This isn't just faster, it's fundamentally different, opening up entirely new ways of solving problems that are currently beyond our reach. But how does this work in practice? Think of a quantum AI as a machine that doesn't just think in the traditional sense, but dreams in quantum states. When faced with a complex problem, like optimizing a global supply chain or designing a new drug, it doesn't follow a linear path. Instead, it explores a vast landscape of possibilities, collapsing its quantum states into the most optimal solution. It's like having a supercharged brainstorming session where every idea is considered simultaneously and the best one emerges naturally. This could revolutionize fields like medicine, logistics, and even creative arts, where the ability to explore countless options quickly could lead to breakthroughs we can't yet imagine. The implications of quantum AI go beyond just solving problems faster. It could fundamentally change how we think about intelligence itself. In the classical world, intelligence is often seen as the ability to process information and make decisions based on clear, logical rules. But in the quantum realm, intelligence might look more like navigating a sea of probabilities, where the best decision isn't always clear-cut. Could this lead to machines that think more like humans, embracing ambiguity and intuition rather than rigid logic? And if so, what does that say about the nature of consciousness itself? Here's where things get even more intriguing. Quantum AI might not just benefit from quantum mechanics, it could also help us unlock its mysteries. Imagine an AI designed to analyze quantum systems, sifting through the vast amounts of data generated by experiments to uncover patterns and connections that human scientists might miss. It could be the key to solving some of the most perplexing puzzles in physics, from the nature of entanglement to the unification of quantum mechanics and gravity. In a way, quantum AI could become a partner in our quest to understand the universe, offering insights that push the boundaries of what we thought was possible. But with great power comes great responsibility. The rise of quantum AI raises important ethical questions. How do we ensure that machines capable of thinking in quantum states make decisions that align with human values? What safeguards do we need to prevent unintended consequences in a world where probabilities rule? These aren't just technical challenges, they're philosophical ones, forcing us to confront what it means to create intelligence that operates beyond our classical understanding. As we stand on the brink of this new frontier, one thing is clear: the fusion of quantum mechanics and artificial intelligence could reshape not just technology, but our very understanding of intelligence, consciousness, and the universe itself. It's a reminder that the quantum world is full of surprises, and that the next great leap forward might come from a machine that thinks in ways we're only beginning to imagine. And as we continue to explore these mysteries, the journey into the quantum realm promises to be as thrilling as it is transformative. Now, let's shift our focus from the dazzling possibilities of quantum mechanics to a topic that's just as important but often overlooked: quantum ethics. Imagine a double-edged sword, its blade gleaming with potential. On one side, it promises to revolutionize medicine, communication, and energy. On the other, it raises profound questions about privacy, security, and who gets to wield its power. This is the essence of quantum ethics, a field that asks not just what we can do with quantum technologies, but what we should do. One of the most pressing ethical concerns revolves around quantum computing and its potential to break traditional encryption. Picture a lock that's been unbreakable for centuries, safeguarding everything from financial transactions to national secrets. Quantum computers, with their ability to perform calculations at unimaginable speeds, could shatter that lock in moments. While this might sound like a breakthrough for cybersecurity, it also opens the door to unprecedented risks. What happens when sensitive data, your medical records, your financial information, even your private communications, can be accessed by anyone with the right quantum tools? The line between progress and vulnerability becomes razor thin, but it's not just about privacy. The rise of quantum technologies also raises questions about control and accessibility. Think of it like this: if quantum computers and communication networks become the new standard, who gets to decide how they're used? Will these powerful tools be available to everyone, or will they become the exclusive domain of governments, corporations, or a select few? The risk of creating a quantum divide, a gap between those who have access to these technologies and those who don't, could deepen existing inequalities, leaving entire populations at a disadvantage. And then there's the question of accountability. Quantum systems are inherently probabilistic, meaning their outcomes aren't always predictable. Imagine a self-driving car powered by a quantum AI. What happens if it makes a decision that leads to harm? Who is responsible, the programmer, the manufacturer, or the machine itself? These aren't just hypothetical scenarios, they're ethical dilemmas that will shape the future of technology and society. But here's the thing: ethics isn't just about identifying problems, it's about finding solutions. By addressing these concerns early, we can steer the development of quantum technologies in a direction that benefits everyone. This means creating frameworks for responsible innovation, ensuring that privacy and security are built into quantum systems from the ground up, and fostering global collaboration to prevent misuse. It's not enough to marvel at the potential of quantum mechanics. We must also ask how it can serve humanity as a whole. As we navigate this uncharted territory, one thing becomes clear: the choices we make today will shape the quantum future. Will we use these technologies to empower individuals and communities, or will we let them become tools of control and division? The answers lie not just in the labs and boardrooms where quantum breakthroughs are being made, but in the conversations we have about ethics, values, and the kind of world we want to create. And as we continue to explore the quantum frontier, these ethical considerations will be just as important as the science itself. The next anomaly we'll examine takes this interconnectedness even further, revealing a universe where the boundaries between technology, ethics, and humanity are more fluid than we think. Now, let's step into the realm of possibility, where the quantum mysteries we've explored might one day revolutionize not just science, but the very way we understand reality itself. Imagine standing before a puzzle, its pieces scattered across a vast table. Each piece represents a quantum anomaly: entanglement, superposition, wave-particle duality, and as you fit them together, a larger picture begins to emerge. But here's the twist: this puzzle has no edges, no final frame. It's infinite, with each new discovery adding more pieces, reshaping the image in ways we can't yet predict. This is the future of quantum reality, a cosmic puzzle where every piece we place changes how we see the whole. What might this future look like? For starters, quantum technologies could transform our everyday lives in ways that feel almost magical. Imagine computers that solve problems in seconds that would take classical machines millions of years, or communication networks so secure that eavesdropping becomes impossible. These aren't distant dreams, they're the first glimpses of a quantum-powered world, where the strange rules of the subatomic realm are harnessed to push the boundaries of what's possible. But the implications go far beyond gadgets and gizmos. Quantum breakthroughs could redefine how we think about existence itself, challenging our most fundamental assumptions about space, time, and even consciousness. Take quantum biology, for example. What if the same principles that allow particles to exist in multiple states at once also play a role in how our brains process information? Could consciousness itself be a quantum phenomenon, with thoughts and decisions emerging from the interplay of probabilities and observations? This idea, while still speculative, hints at a future where the line between mind and matter becomes increasingly blurred, opening up new ways to understand ourselves and our place in the universe. And then there's the tantalizing possibility of quantum gravity, a theory that could finally unite the microscopic world of particles with the cosmic dance of galaxies. Imagine a universe where the force that binds atoms together is the same force that shapes the orbits of planets and the expansion of space-time. Such a breakthrough wouldn't just solve one of the greatest puzzles in physics. It could reveal a deeper, more unified reality where the boundaries between the quantum and the cosmic dissolve. But perhaps the most profound implication of all is how quantum anomalies might reshape our understanding of existence itself. What if the universe isn't a fixed, objective reality, but a dynamic, participatory one where observation and interaction play a fundamental role in shaping what we perceive? This idea, rooted in the observer effect and the many worlds interpretation, suggests that reality might be more like a shared dream than a static stage, with each of us contributing to its unfolding story. As we stand on the brink of this quantum revolution, one thing is clear: the journey is far from over. Every discovery, every anomaly adds a new piece to the puzzle, revealing a universe that's more interconnected, more mysterious, and more beautiful than we ever imagined. And while we may never see the full picture, the act of searching, of fitting those pieces together, is what drives us forward, pushing the boundaries of knowledge and imagination alike. So, what's next? The quantum revolution is just beginning, and the possibilities are as infinite as the puzzle itself. Whether it's unlocking the secrets of dark matter, harnessing the power of quantum AI, or uncovering the true nature of reality, the future promises to be as thrilling as it is unpredictable. And as we continue to explore, to question, and to wonder, one thing is certain: the quantum world will always have more surprises in store, inviting us to dive deeper into the unknown and discover what lies beyond the limits of our understanding. The adventure is just getting started, and the best is yet to come. As we reach the end of this journey through the quantum realm, it's worth pausing to reflect on just how extraordinary these 32 anomalies are. From particles that exist in multiple places at once to black holes that might hold the key to the universe's deepest secrets, each discovery challenges our understanding of reality in ways that are both thrilling and humbling. These aren't just quirks of physics, they're glimpses into a universe that operates on rules far stranger and more beautiful than we ever imagined. Think about it. The Double-Slit Experiment reveals that observation itself can shape reality, while quantum entanglement suggests that particles can communicate instantaneously across vast distances. Schrödinger's cat reminds us that reality might not be fixed until we look at it, and the quantum vacuum hints that even empty space is teeming with energy and possibility. These anomalies don't just defy our everyday intuition. They invite us to rethink what it means to exist, to observe, and to be part of a universe that's far more interconnected than we ever thought. But what does all this mean for us? These discoveries aren't just abstract ideas. They have profound implications for our understanding of everything from technology to consciousness. Quantum computers could revolutionize how we solve problems, while quantum biology might reveal new insights into the nature of life itself. The search for quantum gravity could unite the microscopic and the cosmic, offering a glimpse into the ultimate nature of reality. And yet, for all we've uncovered, the quantum world remains full of mysteries waiting to be explored. The beauty of quantum mechanics lies not just in its strangeness, but in its ability to inspire wonder and curiosity. It reminds us that the universe is a place of endless possibilities, where even the most familiar things like time, space, or matter might be far more complex than they appear. As physicist Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics. And perhaps that's the point. The quantum world isn't meant to be easily understood. It's meant to be questioned, explored, and marveled at. So, what's next? The journey into the quantum realm is far from over. Every anomaly we've explored is a doorway to new questions, new discoveries, and new ways of seeing the universe. Whether you're a seasoned science enthusiast or just beginning to dip your toes into the wonders of physics, there's always more to learn, more to ponder, and more to be amazed by. As we close this chapter, I want to leave you with a thought from Carl Sagan. Somewhere, something incredible is waiting to be known. The quantum world is full of those incredible somethings, and each one invites us to keep questioning, keep exploring, and keep marveling at the mysteries of the universe. If this journey has sparked your curiosity, I'd love to hear your thoughts in the comments below. And if you're hungry for more mind-bending content, don't forget to subscribe and join us as we continue to dive into the strange, beautiful, and endlessly fascinating world of science. The adventure is just beginning.